So now you have all the groundwork you need to be able to understand how to calculate the potential, but now let's actually go through and do a problem with calculating the potential. Now this one is going to be a little bit strange. It's not completely unusual, but it's a little strange because I'm telling you the whole reason we do potentials is so that because sometimes it's difficult to use the electric field. But what we're going to do is we're going to start from the electric field and then determine the potential from that. The reason we're doing that is this will get us the tools that you can then use later to calculate the potential directly. And there are some situations where the easiest approach will be to know what the field is, and then you can calculate the potential. So let's go ahead and get started with this problem. The question is, what is the electric potential for a charged conductive sphere? All right. So this, if it's a charged conductive sphere, let's just go ahead and say it has plus charge. And what do you know about that? You know the charge is going to spread out evenly, but you know it's going to spread out evenly on the surface. So they're trying to get as far away from one another as they can, and they are free to move, and so this is what they do. All right, so what is the electric field, say, for a point? Let's use this radius r0. For r less than r0, we know that the electric field, we can do this Gaussian surface, and we know that E dot dA is equal to the charge enclosed. How much charge is enclosed? 0. So we know that the electric field inside here is equal to 0. And we know that's the field, actually the field that's equal to 0, and not just the flux that's equal to 0, because of the symmetry of the problem. So we know the field is the same everywhere. We know the integral of it is 0. Therefore, the field must be 0. Okay, so E equals 0. Then, meanwhile, we know if we, right here, just outside, we know that our E dot dA, and once again, by symmetry, we know that it's not, E is not changing, so we can pull that right out of the integral. So all we have is 4 pi r0 squared is our area. So E 4 pi r0 squared equals Q enclosed over epsilon 0. So we know that the E, oh, excuse me, let's take, well, I'll put the vector sign in. We don't need it, but okay, so we know that's the electric field, and we know this is in the r hat direction. Once again, we just know that from symmetry, but the magnitude is obviously just the magnitude there. Okay, so there we know. And what do we know then about any point out in space, some point out here, r? We know that, once again, by symmetry, the field is going to be identical at every spot at that radius. And so if we do the Gaussian surface there, we know that E of r, now I'm just talking about the magnitude, is 1 over 4 pi epsilon 0, 1 over, Q over r squared. Okay, so r0 is the radius of this charged conductive sphere. R is just some location out in space. All right, that's what we know. Now what else do we know? When we're talking about potentials, what we know is that minus E dot dl equals from A to B equals VB minus VA. Okay? We know the electric potential at point B minus the electric potential at point A is equal to the line integral of the electric field from point A to B. And once again, we can use any path we want to go from A to B. All right. Okay, so now let's just go ahead and look at this. What if we have a point A right here and a point B that's just inside that surface there? What is E dot dl? Well, E equals 0, so E dot dl is equal to 0. Well, what does that mean? That means that this is equal to 0 in that region. Does it say anything about what the absolute value of VB and VA are? No, it doesn't. The only thing it says is that they are equal to each other. VB and VA are equal. They have the same value inside this sphere. you'll notice there was a bit of a jump right there. I was planning on doing this a different way than your book did, and then when I got done with it, I realized it didn't help as much as I thought it would. So I'm really going to kind of duplicate what your book has done. So what we have just discovered is that the potential from anywhere inside the sphere is equal to 0 up to the very edge. But then let's look at the very edge. Remember, potential is only defined in terms of this difference right here. And just the line integral here. Well, if we are right here, right at the edge of the sphere, and we go to this point 0, do we have any electric field anywhere inside that conductor? No. So what we say is that the potential right here at the edge of this, so what we did before was we went right up to the edge. Now we're actually going to the edge. And we're saying, you know what? We know the potential within this conductor is 0. Therefore, even all the way up to the edge, the potential difference is still going to be 0. So whatever value it is, if this is V versus R, and this is our R0, whatever value it is going to be some value up to that time. And the question, and just so you know what my hang-up was, I tried to set this be a different value than the value that's in the book, and it just, like I said, it just wasn't helpful enough to be worthwhile. So what we're going to do is we aren't going to worry about what that exact value is right now. What we're going to do is we're going to calculate the rest of the potential. Excuse me. So now we're looking at any point, some point out here at R. And we're going to look at this integral. Well, what do we know about R? We know it. What do we know about E? Excuse me. We know it's Q over 4 pi epsilon 0. We know it's in the R hat direction. Therefore, we are going in the R hat direction. And so our dl from this line integral is actually dr. And I can change this from a vector to, I can change this to the dot product, which is just the magnitude of E times dl. So the only thing, dr, excuse me. So the only thing here is a 1 over r squared dr. I'm going from point A to B, and minus this is going to be, now right here at the edge of the sphere, my point B is way out somewhere at r, at big R. And so what is this integral? It's minus q over 4 pi epsilon 0, 1 over r minus 1 over, I'll go ahead and change these limits. What's the point? Oh, the point is this. The point is that it's this b is equal to r. That's point r. There's no 0 there. That's just a point. And the other one is A is equal to R0. So I just did that already in this interval. All right, now here's what we usually do, and this is indeed what the book does. What the book does, it says we can choose this value to be anything we want. The only thing that matters is the difference. Therefore, let's choose it so that this part of it right here is equal to 0. So minus q over 4 pi epsilon 0 r, when r is very far away, i.e. infinity, when r is very far away, we say this will be equal to 0. And then now we don't need to talk in terms of potential difference anymore, because we have set a 0, so everything is measured with respect to that 0. So we are talking about potential difference even when we just say what's the electric potential. So, in this particular case, what does this end up being? It is Q over 4 pi epsilon 0 R0. And you see the signs change there. So what this says is right here we have Q over 4 pi epsilon 0 R0. That's the value right here at the edge of this sphere. And then what happens? Well, if we go a little bit further out, if we just went a little bit further out, what's going to happen to this? It's going to have this extra little bit, this extra 1 over r, that is taken away. You're going to subtract this from the value. So what's going to happen is we're going to go down as 1 over r. And then at some point very far away, this is going to be equal to a very large number, which means this is going to go to 0. And so we have our electric potential as a function of distance goes as this. So there you go. Let's just go ahead and, so now this was right at R0, but what is it at any, well, let's just leave it at that. You now know how to calculate the potential difference between any points from here to here. Okay, so that is, take a look at the example in your book, and I forget what one it is, but actually, yeah, I know this is running a little long already, but I'm going to go ahead and finish this out with one more thing, and that is, what would happen if we shrunk this down? If we shrunk this down to where it was not a conductive sphere, but it was just a point. Well, if it's just a point, there's no such thing as inside the point, so we don't need to worry about this section at all. Instead, this is where 0 starts. And then what is going to be the difference after that? What does Gauss's law tell us the electric field of this is? It's the charge enclosed. And if this is all on one point, the electric field is still the charge enclosed. And so all of this analysis is exactly the same, and we still end up with this expression for the electric field. We have Q over, for the electric potential, 4 pi epsilon 0 R. Yeah, let's just go ahead and leave it at that. All right, so look at those examples in your book. I can't remember what they are, and hopefully this might have made it a little bit clearer.